Okay. So good morning, everybody. Welcome to Luozhou Li's thesis defense. Particular thanks to Carl Bergman and Terry Orlando for being on the committee, and thanks to you all for coming. And especially thanks to Luozhou's lovely family, Mr. and Mrs. Luozhou, and others for making it. So, I'm nervous because this is actually a real camera this time. In our group meetings, we have sometimes my cell phone camera, but this is a proper piece of equipment. So I want to, extend some props to you guys for organizing that. So Luozhou grew up in Hubei province, which is in the central part of China, and received his bachelor in optical electronics from the Luozhou University of Science and Technology in 2009. In his senior year, he was an exchange student at University of Paris, Sud, and in Cambridge in the UK, and then came to join my group in 2010 at Columbia University and received his master's at Columbia in electrical engineering, and then transferred in 2014 to the MIT EECS program. So Luozhou has received a number of recognitions, including the 2013 EIPV and Micrograph Contest Prize and the 2014 SPAE Optics and Photonics Education Scholarship. In addition to this awesome camera, which is being manned by Tom, another props I wanted to mention is Carl Berger just informed me that these donuts are his very favorite. They're definitely so I think you've done your research there too, so congratulations. So Luozhou. I wanted to say Boston cream if So Luozhou's research has focused on fabricating in single crystal diamond a number of different devices. We're going to see some of them for applications in quantum enhanced sensing and information processing. So with that, I'd like to pass it off to Luozhou.
Thank Dirk for the introduction, and good morning, everyone. Thank you for coming to my thesis defense. And today I will talk about my PhD work on diamond nanophotonic devices for quantum information processing. A central aim of quantum information processing is the efficient entanglement of multiple qubit registers. In such entangled systems, the qubits have to interact with each other and at the same time must be controlled individually. Individual control is challenging for these closely spaced qubits, for instance, interact via magnetic dipole coupling. And one promising way to overcome this challenge is to use photons as flying qubits to establish the entanglement between these stationary qubits that are sufficiently spaced. By repeating the entanglement operations multiple times, a large number of qubits could be entangled to form a quantum network. Such a quantum network could enable long-distance quantum state teleportation, complex quantum simulation, distributed quantum computing, and enhanced precision measurement. Several physical systems have been proposed to realize such a quantum network, including trapped ions, neutral atoms, and quantum dots. Recently, a very promising qubit candidate has been used in quantum information processing protocols, that is, negative charged nitrogen vacancy centers in diamond, or we refer it as NV. My talk will first introduce NVs and the challenges in using them for quantum information processing. Then I will talk about photonic nanostructures and how the membrane-based photonic structures would serve the challenges that we face in using NVs. Because there's no commercially available diamond membranes, we have to develop and apply different ways to fabricate them. I have also developed a silicon mask lithography for patterning nanostructures into these diamond membranes. The resultant diamond devices has the potential to advance most of the established quantum network protocols. And in the end, I would conclude my talk and mention what I and my group mates plan to do in the near future. In diamond, there are many atomic impurities. During my thesis, I mainly worked with nitrogen vacancy centers that can be found in this naturally yellow diamond. The NV is composed of a substitutional nitrogen impurity and a lax labor vacancy. It has a long spin coherence time because it lives in a spin-free environment, as the diamond is composed of 99% carbon-12, which has a nuclear spin 0. And spin-dependent fluorescence allows the NV electron spins to be easily initialized and read out through the standard confocal microscope. In the simplified energy level diagram, we consider 3 electronic states. One is ground state, one is excited state, and third is a metal stable state. If we look at the ground state more closely, it has an associated spin triplet, which has an energy difference between ms equal to 0 state and ms equal to plus minus 1 state of 2.88 gigahertz, that is in microwave range. And the degeneracy of ms equal to plus and minus 1 state can be lifted by an external magnetic field via inducing a Zeeman shift. And we are able to use 2 of these 3 sublevels to construct a qubit. And in our case, we use the ms equal to 0 state as quantum state 0 and ms equal to minus 1 state as quantum state 1. Quantum state 0 is brighter than quantum state 1 because NV has a spin-dependent sharing into the dark metal stable state. Here is one example of a spin measurement. By resiliently applying a microwave pulse, we are able to oscillate the NV quantum state between 0 and 1. And the takeaway message from this slide is that NV is a good spin qubit. Not only NV centers can exist naturally, but also we are able to produce them either via during the chemical vapor deposition growth process, or by nitrogen ion implantation and annealing. Excited by the green laser, the NV electrons will be pumped from ground state to excited state and decay back to the ground state with a photon emission. And in the spectrum, we can say that these NV emissions will not only be in the 0 photon line, but also via a phonon interaction through the phonon sideband. And the figure on the top right corner is a scanning confocal intensity plot of a diamond sample. And this sample was implanted with 10 to the 9th nitrogen atom per square centimeter. And after annealing, we are able to say these sparsely distributed NV centers. And these are confirmed, these will be confirmed to be single photon emitters, and which eventually contribute to a spin photon interface between NV and photons. By splitting the photons from this bright spot onto a 50-50 beam splitter and detected at 2 pods with 2 detectors, and we recorded the correlation histogram of detected photons, and the expected value of second-order correlation function at 0 is given by 1 minus 1 over n, where n refers to the number of single emitters. With a single emitter, the G20 value will be 0, and with 2 emitters, this value will be 0.5. In real experiments, their NV emission is often accompanied with some background fluorescence from diamond. That's why the G2 dip is normally below 0, even it's slightly below 0, but still slightly above 0, but still below 0.5, even for a single photon emitter. And we readily use this measurement to determine a single NV spin qubit. And this single spin qubit can be used in quantum information processing. And one example is the entanglement of two NV memories that are 3 meters apart from each other. And the entanglement was established by flying qubit photons. This experiment was demonstrated 2 years ago by Bernier and others. And in their experiment, the NVs are first prepared in superposition state, and we denote them as spin up and spin down. And then a state-selective resonant laser pulse would create the spin-photon entanglement between NV and spontaneous emitted photons. And these photons are overlapped on the beam splitter and detected at two output ports. Both spins are flipped, and the NV excitation was carried out a second time. The detection of one photon for each excitation cycle heralds the entanglement of two NV electron spins. If we repeat this entanglement operation many times for many NVs, and in principle, we are able to entangle a large number of NV qubits and to establish a quantum network. But the problem is the entanglement generation rate for this experiment is very low, only one entangled pair per several minutes. That's not good. This brings us to the summary of advantages and disadvantages of NVs.
Sorry, can you just go back one slide? Oh, go back two, I guess. And then the last, all the way through it. There was just a question on the notation. So this notation, up 1, down 0, is that you're just saying spin up is, you call that also 1? Or are those two different qubits?
Spin up and spin down as a quantum state for NV, and 1 and 2 are denoting whether there is one photon or no photon. Yeah, sorry for the confusion.
1 and 0, you mean?
Yeah, sorry. 1 and 0 means there's photon, no photon. So the advantage of NV centers is optically address the spin initialization and readout and non-spin coherence time. And disadvantage is also obvious. Overall collection efficiency from a single NV is low. That's because the index contrast between the diamond and air interface. For optical entanglement of two NVs, we also the count rate is only about 300 kilocounts per second. And for optical entanglement of two NVs, the photon emission need to be a coherent process. That means the photons must be in the zero photon line. And in the case of NV, we define this ratio as Debye-Waller factor. And this Debye-Waller factor is also very low for NV. It's only about 3%. That means only 3% of photons are emitted through zero photon line. And this is the reason for this inefficient photon spin interface is the reason for low entanglement generation rate. And to solve this problem, we can either improve the overall collection efficiency or enhance the NV-ZPL emission. The improvement of NV optical property can be achieved by fabricating diamond nanostructures. Many research groups have pursued different ways of fabricating photonic structures in bulk diamond. And for instance, this one is a silicon dioxide grating embedded in a silver mirror helps to excite and collect the photoluminescence from a single NV center. Their collected count rate is about 0.7 milliarcons per second. And this one is a diamond solid immersion lens, which gives 1.1 milliarcons per second. It has a successful implementation in quantum entanglement and teleportation applications. And with tapered vertical pillars, the collected count rate can be 1.7 milliarcons per second. The people has used that for near-surface sensing applications. The drawback of these bulk diamond devices is also obvious, that there's although we can collect photons through one side, but also the other side is leaking. The photons will leak into the substrate on the opposite side of the collection path. That means we need a better dielectric environment to control and guide the photon emission pattern, and which calls for the the membrane-based devices. In thin membranes, optical guidance and control of light emission and propagation is most straightforward. And in this image, you can see a dielectric membrane. This is a mode pattern of a dielectric membrane with a simulated continuous wave plane wave source at the left end. And the thickness of this dielectric membrane should be on the order of half of the effective wavelength to achieve single mode guidance. And these membranes have successful implementation in quantum dot research. There are two examples. One is circular gratings, and light emitted from quantum dot scattered at air slits, and a majority of light emission can be collected by a low numerical aperture objective lens in the far field. And the second example is photonic crystal cavities. Photonic crystal can confine the emission from a quantum dot in the vertical direction by total internal reflection, and in the horizontal direction by distributed Bragg reflection. And an additional defect inside of the photonic crystal at a quantum dot position would would enhance the local density of electromagnetic states, and thus increase the spontaneous emission rate at the resonant at a resonant mode. Unfortunately, single mode diamonds are not commercially available, and before we are able to fabricate these devices into the diamond, we need to first figure out ways to produce diamond membranes ourselves. Diamond could be grown by chemical vapor deposition, but 200 nanometer high quality single crystal diamond membranes are not possible to grow so far. And I will now introduce 3 different approaches that we developed and applied for diamond membrane fabrication. And we first tried crystal ion slicing, which was a similar technique as smart card technique for silicon on insulator wafers. And this project was led by Ophir, our former postdoc. And first we implanted helium ions to create a heavily damaged layer 2.5 micron below the diamond surface. And then we patterned squares by using optical lithography and metal lift-off techniques. And a subsequent oxygen plasma etching would transfer this metal mask into the diamond. After annealing, this heavily damaged layer turns to a graphitic layer, which can be easily removed by acid etching. And eventually, we are able to flip them over and use oxygen plasma to thin them down further and to achieve 200 nanometer desired thickness.
How wide?
It's about 100 micron times 100 micron.
How thick?
Eventually, they became 200 nanometers.
What energy healing lines do we use?
It's about 1.6 million EV. And this is a resultant ion sliced diamond membrane still attached to the bulk diamond. And this is a transferred one onto other substrate. And we measured the optical property of this transferred diamond membrane. Turns out that there is NVZPL, that's good. But the bad news is that there's too much background fluorescence. This background prevents us, means that this method does not produce diamond membranes that are of high enough quality for our applications.
Sorry, what's the y-axis? Intensity of what?
PL intensity, photoluminescence.
And what's the temperature if you did the measurement?
It's room temperature. We also tried a different way of fabricating vertical diamond membranes that avoids ion implantation. So we first pattern HSQ strips on top of a bulk diamond, and we using lithography, and then we use oxygen plasma to etch them down to produce vertical diamond membranes. But unfortunately, we are only to be able to etch 4 micron deep without degrading the HSQ mask too much. And what we have to do for our applications, the deeper we etch, the better. And to go deeper, we developed a way that is similar to silicon deep reactive ion etching, also known as Bosch process. And we deposit 50 nanometer chrome from both sides at 45-degree angle. And this chrome layer would protect the sideboard and also add the mask on top of the membrane. Because these membranes are closely spaced with each other, and the chrome deposition will not go to the bottom of the diamond membrane. In this way, we can etch down further using oxygen plasma. By repeating this deposition and etching steps multiple times, we are able to produce vertical diamond nanoslabs as you can see here, the top view of this vertical diamond nanoslabs, and also the side view of the cross-section gives us the height information. It's about 10 micron in height. And then we can break off these diamond membranes and transfer them onto other substrate. And this SEM image is a diamond nanoslabs on top of a silicon standoff posts. Let's see how good their optical properties are compared to the previous method. And the optical measurement is in close collaboration with our another former postdoc, Jonathan. And this is a confocal scan of a diamond nanoslab still attached on top of the bulk diamond. And this bright spot is a single nitrogen NV center, which was confirmed by second-order autocorrelation measurement and also the spectrum. It has a characteristic zero phonon line and a broad phonon sideband from 650 to 800 nanometer. And we also checked the optical property after these diamond nanoslabs are transferred onto a cover glass. And this is a confocal scan again, but for the transferred diamond nanoslabs. And a G2 deep below 0.5 indicate that this NV inside of the green square is a single photon emitter. And so far, we can claim that this method produces a more clean diamond membrane, which has better optical property compared to the crystal ion sliced diamond membranes.
Sorry, what is the left axis?
This one?
Yeah, the number of events.
The delay between
The y-axis side.
photon counted per second.
That's I think for the left-hand image, but for the right-hand image, what is it that you're plotting?
Oh, sorry. This is a number of events that's basically detected photon numbers.
Okay.
And there are other bright spots on there. Are those NV centers? Or?
Yeah, they are NV centers as well.
And do they have similar properties?
Yeah.
Okay.
Yeah. And these membranes are also large enough for us to pattern photonic crystal cavities. And this image gives you an idea how we pattern photonic crystal cavities with focused ion beam meaning. And we also call focused ion beam as FIB. And unfortunately, these cavities does not give us any cavity resonance. That's because the FIB causes surface damage. FIB causes surface damage, as you can see in this image. We zoom in and examine the edge of the diamond membrane milled by FIB using a transmission electron microscope. There is an amorphous layer that is about 11 nanometer in thickness. And this amorphous layer scatters light randomly and prevents the cavity resonance from forming. And these diamond membranes are also of irregular shapes and were no more than 20 microns in natural dimensions. And in summary, these diamond nanoslabs have a puny material property, but they are still not good enough for further photonic device fabrication. At the same time, we were trying to pursuing this approach. A new opportunity had emerged since Element 6, a CVD diamond growth company, was able to provide 5-micron diamond membranes instead of 300 microns bulk diamond that they previously had. That provides us an opportunity to thin the 5-micron diamond membranes down to 200 nanometer directly. But for these 5-micron diamond membranes, there are still challenges. The first one is surface roughness. After long-time oxygen plasma etching, the surface would become too rough. And the second problem is the thickness variation. And after thinning them down, we find huge surface, the thickness variation for even hundreds of microns in natural dimensions. And we and others, these other groups, have solved the surface roughness problem by using chlorine plasma etching, which turned to etch isotropically and smooth the diamond surface. And we solved the thickness uniformity problems by thinning this diamond membrane down to 300, 400 nanometers, and then break them into even smaller pieces using a tungsten tip. And after that, we thin these membranes further down to 200 nanometers individually. This is a resultant diamond membrane produced in RIE polishing way. And the thickness is about 30 nanometer within desired 200 nanometer. And the room mean square surface roughness decreased from 0.4 nanometer to 0.5 nanometer to 0.25 nanometer after 10 minutes chlorine etching, which was not only observed by us, but also reported by this paper. So far, we have developed a method that is good enough to produce diamond membranes for further photonic crystal fabrication. The next challenge we faced was how to pattern these rather small diamond membranes with nanostructures. And I will introduce a new form of lithography that I developed. It's challenging to pattern on these 200 nanometer diamond membranes with traditional fabrication methods. The first reason is that wet etching would be a problem. If we spin coat these diamond membranes, they may just fly away. And if we put them in a beaker for liquid development, they may just end up somewhere in the beaker and you will never find it back. Also, electron ion beam irradiation may affect NV charge state or even damage NVs. Our solution is to fabricate high-quality etch masks somewhere on other substrate and then move them onto the diamond membrane. And we tested a lot of materials. Silicon was proven to be the best, as I will tell you why in the following 3 slides. Silicon masks can be produced from silicon on insulator wafers, as there exist mature fabrication technologies to make it happen. And this is a side view of a silicon membrane on top of a dioxide layer, and oxide layer was removed by HF, and that's also why the color looks lighter than the bulk. And these membranes are attached to the bulk substrate by these seam bridges at 4 corners. And these seam bridges would be easily broken if we attach the sample with a PDMS adhesive attached by a tungsten tip. And this is so the PDMS adhesive touches silicon mask. Adhesion between PDMS and silicon mask is strong enough, and this silicon membrane would be ripped from the parent chip. And this is a PDMS adhesive with an attached silicon membrane. Then we release the silicon membrane onto a diamond membrane by rolling over the PDMS and then lift the PDMS back up. This is an optical image of a silicon mask on top of a diamond membrane. The diamond membrane has a much smaller size in natural dimension. And we use the oxygen plasma to transfer the patterns from silicon mask into the diamond membrane. And after removing the silicon mask, we use SF6 plasma etching to lightly remove the silicon under this and suspended diamond photonic devices at device locations. This is a SEM image of resultant photonic device. It happens to be a 2-dimensional photonic crystal cavity with 7 missing holes to form a resonance. And this method is not only limited to this specific pattern. It can be used for any patterns as long as they can be prepared in a contiguous mask.
Sorry, I missed something I was taking notes. What was the SF6 for?
The SF6 removed the bottom silicon to suspend the diamond membrane at device locations.
So the diamond membrane is put down on silicon, and then silicon is put on top of the diamond membrane.
Yeah. And then we use oxygen plasma to transfer the pattern from silicon into diamond. And we mechanically remove the silicon mask, and then we use SF6 to undercut the bottom silicon.
All the way, or just partially?
Just partially at the device locations. Silicon is a good etch mask material for oxygen plasma etching of diamond. And as you can see, the holes are uniform and the side walls are vertical. we also did a test by placing a silicon membrane on top of a bulk diamond. And we tried to etch down until we say the degradation of silicon mask. The etch selectivity is about 38 to 1. And in this case, we used a 220 nanometer silicon to etch into 8.5 micron diamond. So then there are also a few other photon devices that I patterned using this silicon mask lithography. The first one is diamond micro waveguide that my lab mates, Rich and Sarah, has used them in their separate experiments for fiber and waveguide integration to form quantum networks. And also circular photonic crystal cavities and one-dimensional photonic crystal cavities with circular holes. Right now, we have a way to pattern these diamond pattern nanostructures into diamond membranes. And we would like to say how good they are. And there are two representative devices. One is Bose-I grating that improve the overall collection efficiency from a single NV. And this project is in close collaboration with Ed. These Bose-I gratings consist of concentric slits fully etched into diamond membranes. And the periodicity of these slits satisfies second-order Bragg condition. And we placed these Bose-I gratings onto a cover glass, and we find that the photoluminescence from a single NV would majority emitted through a cover glass into an oil objective lens collected by an oil objective lens. That's about 70% of light. Then we fabricate this diamond membrane with Bose-I gratings a lot and place them onto microwave strip line for both optical and spin measurement.
How do you align the bullseye with the NV center?
Under an a line of Bose-I with NV center, we don't align. We just find where the Bose-I contains an NV center.
Okay, gotcha.
This is a SEM image of the resultant Bose-I gratings. And the photoluminescence shows us that this bright spot, and this bright spot was confirmed to be a single NV center by both second-order autocorrelation measurement and spectral measurement. We also analyzed the Bose-I's far-field mode pattern. And as you can see, there is strong intensity within numerical aperture of 0.7. Comparatively, for an unpatterned diamond membrane, the photon emission is primarily into the higher NA mode. And the simulation results also are also consistent with these experimental results. To estimate the saturated count rate from a single NV center inside of Bose-I, we have measured the count rate as a function of excitation laser power. And this blue line is measured here, which gives a linear background line. And the green line is measured at the NV position. We subtract the total count rate. We subtract the background from the total count rate. Then we fit the subtracted count rate with this saturation curve fitting equation. And this was commonly used. This is commonly used in quantum dot and NV communities. And the estimated saturated count rate is about 4.5 millicounts per second at saturation power at about 80 megawatt. And this is a record high country collected from a single NV. It represents 4 times higher collection efficiency than the diamond solid immersion lens, and has a potential to increase the entanglement generation rate by 16 times. But 16 times is not good enough. And if we look at the NV spectrum, bullseye enhance the NV spectrum over the whole wavelength. But what we really need is to increase the NV-ZPL emission by 3 or 4 order of magnitude, because that's the only use for photons for our quantum entanglement and other experiments, which calls for a coherent structure, optical cavities. The cavity project is in close collaboration with Tim and Ed. When an NV is placed inside of a cavity, its local density of electromagnetic states would be increased, and the spontaneous emission rate into the cavity mode is given by this equation. And rate enhancement is essentially proportional to the ratio of quality factor over mode volume. And the quality factor quantifies the length of time a photon is trapped inside of a cavity. And this rate enhancement falls off as the spectral detuning of the NV-ZPL with respect to the cavity resonance. And also, it falls off especially for the NV-ZPL with respect to the cavity mode maxima. And in case of NV center, and when the cavity is overlapping with NV-ZPL, it will be greatly enhanced by tens and hundreds of times. And this means we can potentially increase entanglement generation rate by 3 or 4 order of magnitude. Here are some of more commonly used nano cavities with their respective quality factor and mode volume. As you can see, the photonic crystal cavities has the largest Q over V ratio. That's also why other groups, such as Nanchar, Luken, and Park groups at Harvard, and Farion formerly at HB and Bachelor in Germany, they are also pursuing the photonic crystal cavity fabrication. We used one-dimensional photonic crystal cavities, and this consists of a single mode waveguide with 40 edged holes, which serves as distributed Bragg reflectors on both ends. And here is a plot of the lattice constant as a function versus the lattice index. And in the cavity region, the lattice constant decreased from the baseline to by about 10% to form a cavity. And this cavity confines an optical mode, as you can see in this energy density plot. This is a fundamental mode of a photonic crystal cavity. We optimize the quality factor by varying the width and the height of the air slits. And the highest Q we got is well over 500,000. And experimentally, we are not able to achieve such a high Q due to fabrication problems. The fabrication begins by thinning a 5-micron diamond membrane to 200 nanometers, and then we implant nitrogen vacancy centers by nitrogen ion implantation and annealing steps. Then we transfer the silicon mask onto the diamond membrane. This is an SEM image of the silicon mask on top of diamond membrane. Then we use the oxygen plasma to etch these patterns into the diamond membrane. The first purple color is the silicon mask on top, and the bottom is the diamond membrane after etching. Then we removed the silicon mask mechanically, and this is a resultant one-dimensional photonic crystal cavity taken by SEM. Then we transferred these diamond membranes with photonic crystal patterns onto a new silicon wafer by PDMS transfer, which is a method that I previously introduced. And this is a diamond membrane on top of a new silicon wafer. And silicon wafer has ridges of silicon that act as spacers for diamond membrane, so that these diamond membranes are suspended in air 2 microns from the bottom for cavity measurements. And this, in the recessed regions, platinum is deposited there, which serves as a microwave strip line for coherent spin control. This is an overview of our device with 2 wire-bonded pads, and the microwave current is passing through here. And these 2 other pads are reserved for DC star tuning, which haven't been used in our current experiment yet. And also we have a close-up SEM image of the photonic crystal cavities on top of these ridges of silicon with microwave strip line under this. We tested these cavities using a scanning confocal microscope with 532 nanometer excitation laser, and the collection is using the same objective lens. The broad full-on sideband of NV provides an internal light source for our cavity measurement, which allows us to simply record the photoluminescence to find the cavity resonance. And this is one of the fundamental modes that we found for our photonic crystal cavity. It's approaching 10,000. It happens to be a record high quality factor for diamond photonic crystal cavity fabricated for this spectral range. Here is a scanning confocal microscope image of a diamond sample. We can see these cavities as red dotted streets. And we also have NV centers as bright spots. And these NV centers are confirmed to be single photon emitters by second order autocorrelation measurement. And these NV centers are randomly distributed inside of diamond membrane. Sometimes we get lucky, we find this NV cavity system A, which have a bright NV center inside of a photonic crystal cavity. And the spin property of this NV center was also confirmed to be good. It was measured by my colleague Edward, and the spin coherence time is longer than 200 microseconds, which proves that our fabrication process does not degrade the NV spin properties much. For NV cavity system A, if we take spectrum using a high-resolution spectrometer grading, we are able to see a cavity resonance with a quality factor about 1700 and EX-EY transitions that are strings splitted by the internal stress inside of our sample to be the 2 ZPL transitions. And as we inject xenon gas at a cryogenic temperature, this xenon gas would condense on top of photonic crystal cavity, thus increase the effective refractive index of the diamond that can be seen by the cavity. The cavity resonance would shift to the red in the spectrum. It first overlaps with EY transition And when EY transition is on resonance, it gives a Purcell factor enhancement of 17. Then it redshifts further and overlaps with EX transition and enhance the EX ZPL transition as well. And the overlap factor of this for both two transitions is not high. It's the overlap factor is defined by the experimental Purcell factor over the theoretical Purcell factor. The reason why the overlap factor is not high is because the NVs are too sparse on this sample. It's also difficult for us to find many devices with good NV cavity spatial overlap. So to solve this problem, we have prepared a larger sample with 10 times higher NV density, and in which we find a NV cavity system B, and with an optical quality factor about 3,300. And this is a ZPL that is off resonance. And this is the ZPL on resonance with the cavity. And as you can see, there is a huge difference between the ZPL on resonance and off resonance. And we also check the lifetime of NV center. And for the off resonance case, it's about 18 nanoseconds. When the NV ZPL is on resonance, the lifetime decreased to 6.7 nanoseconds. And by using both intensity and lifetime data, we are able to deduce the original Debye-Waller factor for this ZPL, and also the Purcell factor for the rate enhancement. The original Debye-Waller factor is about 1.9%, and Purcell factor enhancement is over 60. And with this high-resolution grating, it only has a spectral range of about 50 nanometer. We are not able to say the overall view of both NVZPL and full-on sideband. So we switch to a lower.
I thought go back. The Q of the, I thought was higher on system A than B.
Oh, for system B, it's 3,300.
And this was about 9,000.
And for system A, it's about
17. I'm
7.
sorry, I was
Yeah.
thinking of the previous. Okay, now it makes sense. Sorry.
With a lower resolution spectrum grating, we are able to say both NVZPL and full-on sideband. NVZPL is a sharp line, and full-on sideband is barely visible. There's over 55% of photons emitted through NVZPL. As a reminder, this is a spectrum of native NV inside a bulk diamond. The NVZPL only occupies 2 or 3% of the overall emission. And this NV cavity system A efficiently channels the NV photoluminescence into the coherent ZPL transition. That this bright line is exactly what we want for as an efficient spin-photon interface for building quantum networks. Then I will conclude my talk, and my goal of PhD is to achieve efficient spin-photon interface. And for that, I first did material preparation, that is fabrication of 200 nanometer diamond membranes. Then I developed a new lithography method that can etch its nanostructures into these diamond membranes. The resultant device 1, that is bullseye grating, increased the overall collection efficiency, and the photonic crystal cavities enhanced the NVZPL a lot. At the same time, when I were working on the efficient spin-photon interface, my colleagues, Sarah and team, have successfully coupled NV centers into a silicon nitride waveguide and achieved the photon transmission. And also, our joint effort between England and Bergman groups has proven that we are able to fabricate the on-chip, high-efficient superconducting nanowire detectors. Moving forward, we would like to merge this effort to produce entanglement generation rate faster than 1,000 counts per second to beat the decoherence rate. Then we would like to scale up the number of entangled quantum registers. Besides the work I described so far, I also had the opportunity to participate some other diamond-related projects, also contribute to spin photon interface for quantum networks. The first is Rich used my fabricated diamond nanowires to couple with fiber for fiber-based quantum networks, and Sarah used them for waveguide-based quantum networks. And I also helped EECS to precisionally implant NV where we want. And we also developed triangular nanobeam waveguide networks. And Matt and I also would like to use the high-purity diamond nanocrystals that I fabricated as hybrid quantum nodes for quantum networks. I also had the opportunity to fabricate silicon photonic devices for graphene-related projects. Yuan Da, Ren Jie, and Xue Tao used my device for their experiments. And at the very end, I would like to thank everybody who are involved on these projects. And specifically, I would like to thank my supervisor, Professor Dirk England, who guided me during the whole PhD period. And I would also like to thank the two colleagues that I worked most closely with for this project. One is Tim, the other is Ed. And I also like to thank the whole England group and our collaborators at Brookhaven National Laboratory, as well as these funding agencies for the support. And thank you for your attention, and I'm happy to take your questions.
Okay, thank you very much, Luozhou. Okay, so we have a couple of minutes for questions.
Can you go to slide 40? It looks like you have two dots there that are close to each other. Am I correct in seeing that? Is that bigger than the cavity? I realize the cavity spacing is around the middle. Is that roughly the size of the cavity spacing? And
the cavity.
I'm just curious if at any time you're lucky enough to have two of the dots. I realize that would be a rare event, but just curious if that ever happened.
Well, actually, for these two dots, only this one is very close to the cavity mode maximal. The other one is barely inside of the cavity, because the cavity the cavity it looks like cavity is this long, but the real cavity mode only confined here.
Sure. So it's about a micron, right?
Yeah.
Any other questions? Giving you easy time.
We'll get a chance later on.
Okay. Seems like people want to get to the closed session. All right, so if there are no further questions, that concludes the open part of this defense. So thanks very much.